Hi everyone, my name's Jeff Watchhorn. I'm a PhD student with the Frank Gu Lab at the University of Toronto, and I'm making this video to talk to you a little bit about my current work, which is looking at understanding the molecular mechanisms behind mucoadhesion. So without any further ado, we'll get right into the presentation. So the title is Disco NMR, a footloose approach to understanding the molecular mechanism of mucoadhesion. Mucoadhesion is this strategy that people use with synthetic materials and polymers to try and extend the residence time of synthetic materials in vivo in mucosal systems, as well as improve physiological effect and stuff like that. There are a lot of different strategies to do this, which are outlined on this slide. And there are a lot of hypotheses kind of around how these work. And so the current issue is that, well, there are these hypotheses that exist. The hypotheses are not complete. So the understanding of how these actually work in vivo is not perfectly modeled. In fact, there's a lot of gaps in existing models, and often different facets of different models need to be combined to even get some semblance of accuracy. And so with this in mind, we developed Disco. No, it's not the dance craze everybody's familiar with. It's actually a type of NMR. It's direct saturation compensated transfer difference NMR. And so what this is a refinement of existing NMR strategies to look at binding and transfer between analytes that are macromolecules specifically. And so we had a hypothesis about how this would work, and we went and tested it with our model system, polyacrylic acid, and we were actually able to tease out the binding of these molecules and how the interaction works. This is what polyacrylic acid looks like in NMR if you haven't seen it before. And basically, we were able to isolate just a binding signal that only is a function of transfer between close molecules that would only occur as a function of binding. And so with this result, we were really excited. So we went on to quantify this and start looking at how molecules bind. And so with polyacrylic acid, we were able to make this fingerprint. And we were able to confirm some hypotheses from previous literature that suggested that the way that polyacrylic acid binds is through backbone interactions and through chain interpenetration. And that's what we observed when we finished this. So that was a really exciting result, and with this we decided to continue and look at other systems. So we started mapping other polymers, and we found some really interesting results. So we looked at cellulose because we can modify cellulose in different ways, and that can change how mucoadhesion is achieved. And we found that when you do that, not only can you achieve mucoadhesion, but it does it in very distinct ways depending on how you modify these. And so this opens up a whole other area that we're currently investigating on the physiological impact. So does mucoadhesion through chain interpenetration influence mucosal layers in the same way that polar binding from hydrogen bonding will influence them? So the ultimate goal of all this is to start guiding development. So now that we have an understanding of how all these things work, or at least at a molecular level, the ways that these can work, we can start creating designed polymers, ones that interact in specific ways to achieve specific goals in terms of physiological compatibility, adhesive strength, and all that good stuff. So that's the end. I'd just like to thank everybody for your time, and please, if you have any questions at all, reach out to me. I love to talk about this kind of stuff. Thanks a lot.